Welcome back to Control System Lectures. In this video I'm going to present an introduction to system stability and control. Before we begin, let's start by defining stability. Stability is a measure of the tendency of a system's response to return to zero after being disturbed. If a system is exposed, say, to an impulse function, for example you hit it with a hammer, and the system response equals zero as time approaches infinity, then this is a system that is considered stable. If instead the response blows up to infinity, then the system is unstable. Another way you might see this explained is that for a stable system, a bounded input produces a bounded output, or BIBO stability, bounded input, bounded output, which means that the only way to get an infinite output is to put in an infinite input. I think the easiest way to grasp this concept is with a classic example. Take a system that consists of a small ball that sits at the bottom of a valley. The ball is initially at rest at the equilibrium point at the bottom of the valley. If the ball is disturbed, say with a force that pushes it away from its equilibrium point, then the ball will start to oscillate, and if there's friction, eventually come to rest back at the equilibrium point. This is a stable system. However, if you were to take the ball and place it on top of a mountain and perform the same experiment, you'll see that this is an unstable system. The ball is initially at rest at the equilibrium point at the top of the mountain. However, once it's disturbed from this point, it will roll down the hill away from the equilibrium. This is very much similar to balancing something on its end, like an egg. It can be done, but since it's unstable, it is susceptible to disturbances and will fall over. As you can imagine, there is some delineation between having a system that is stable and one that is unstable. In the case of the ball, we can visualize this as a flat table that goes on for infinity, or halfway between these two different scenarios. We can see that if the table slopes up ever so slightly on each side, then the ball will eventually come back to rest at the starting point after it's been disturbed. This is a stable system. If the table ever so slightly slopes down, then when the ball is disturbed, it will continue off into infinity, and this is an unstable system. We'll get back to this idea of a point between stable and unstable systems later on in this video. For now, let's take a second example which I think is a little bit more practical than just a ball sitting at the bottom of a valley. I want to show you why there's an inherent stability in the shape of a dart. A traditional dart has a lot of mass at the tip, which skews the center of gravity towards the front of the dart. And it also has flights on the back end of the dart. These are just like feathers on an arrow, and this skews the center of pressure towards the aft end. If we look at this arrow in equilibrium during flight, that is when it's flying straight and level through the air, there are no aerodynamic forces perpendicular to the dart shaft. You can visualize this easier by looking at the dart head on. You can see that both the dart's shaft and the flights on the aft end are both aligned with the air and don't produce any torque about the center of gravity. But what if the dart is disturbed off its equilibrium flight path? And this can be either from an initial rotation given by the thrower or from wind gusts as it flies through the air. Then the dart would be in a position relative to its flight path that looks something a bit like this. In this case, the air pressure acting on the flights will generate a restoring torque about the center of gravity in the direction that causes the back end of the dart to line back up with the air currents. And the dart will oscillate back and forth about this equilibrium point until the oscillations are damped from the loss of energy through friction. This is similar to a weather vane that rotates back and forth to align itself with the wind. This system is stable because the torque generated by the air pressure tends to rotate the dart back to its starting equilibrium point. Alternatively, we can see that we can make the dart unstable by moving the center of gravity further towards the back of the dart and moving the center of pressure forward to the front of the dart. This can be demonstrated by trying to throw a dart backwards. This causes an unstable situation because this puts the center of pressure in front of the center of gravity, which I'll show graphically here shortly. The dart, though, still has an equilibrium point, and that's when the velocity vector is parallel to the dart. And you can still see this from the head-on view that shows that the flights are still lined up with the air currents. The difference comes, though, when the dart is disturbed off its equilibrium point. Now the air pressure on the flights tend to generate a diverging torque about the center of gravity, which causes the front end of the dart to flip away from its starting equilibrium position. And that's why attempting to throw a dart backwards causes it to flip around in the air. But just like with the ball lying on a flat table, there is a point where you could place the flights that would delineate between a stable system and an unstable system. For a dart, this is when the center of pressure and the center of gravity coincide. In this case, no aerodynamic torque is generated, regardless of the orientation of the dart relative to its flight path. Practically speaking, though, if we move the flights so that the center of pressure is ever so slightly aft of the center of gravity, then the dart will be stable. And the reason is because this will still generate a restoring torque, although very small. But this brings up an interesting question. How stable is stable enough? As an engineer, you aren't just concerned with building a stable system. You also want to ensure that the system has enough stability margin to be able to handle small parameter changes in the system's transfer function. Now, these small changes might come about for a variety of reasons, and I'll use this dart example to illustrate two of them. When manufacturing darts, you might not be able to reproduce each one with the exact same center of gravity or center of pressure. Therefore, there's going to be some uncertainty in where those parameters exist on any given dart. Also, the characteristics of the dart could change over time. For example, dropping the dart could bend the flights, which will change the center of pressure or chip off part of the mass, causing the center of gravity to change. In order to have a robust system that can handle variations in these parameters, you have to add margin to your design. But there's another reason. Adding stability to your design also decreases the impact that disturbances have on the system. We can see this with the ball example here. By increasing the steepness of the valley, or adding stability, the same disturbance force will result in a smaller magnitude of the oscillations. So you can imagine that if you flicked each of these three balls in these three different cases, they might have responses that look similar to these. So now you might be thinking, well, why not design the system to have huge stability margins? If a little stability is good, then a lot of stability might be great. Well, this might not be a good solution either. The reason is that just like a stable system won't respond much to disturbances, it's also not going to respond much to actual commands either. For example, a very stable airplane seems like a good idea. However, the more stable an airplane is, the slower it will respond to pilot commands, because it won't want to move away from its equilibrium point. So far, what we've looked here are open-loop responses of a system. That is the response of a system due to its inherent passive design. And an open-loop system can be inherently stable, like in the case of the ball inside the valley. But what happens if the inherent design is unstable, like the case of the ball sitting on top of a mountain? Well, the system can be made stable by active control means. And this is one of the jobs of a control engineer. We'll spend a lot of time on this in other videos, so I just want to quickly touch on it here. If you were given this unstable open-loop system, you can make it stable by adding feedback control. I'll start by drawing a block diagram for a typical control system. The plant consists of the ball and the mountain, and the output of the plant is the horizontal position of the ball. I want to measure the position of the ball with a sensor and then feed back that measured position. My reference position is 0 since I want the ball to stay right at the top of the mountain. I can generate an error term which is fed into a controller, and the controller can create commands that are fed into some actuator that affects the ball's position. So let's go ahead and populate this. To measure the position of the ball, I think I'd use maybe a radar gun that would bounce a signal off the ball and measure the time it takes to return. I'll need one of these on each side since the ball can roll down either side of the mountain. And I can write the transfer function for the radar gun in my block diagram. Now for the actuator, maybe I could use variable speed fans, one on either side that I can control the amount of wind that each one produces, which I can use to generate a force on the ball to blow it back up the hill. And I'll put the transfer function for the fan in the spot for the actuator. Now for the controller, I could just use a computer, and it would take inputs from the radar gun and then feed the error term through a PID controller that'll generate commands to go to the fan. Don't worry too much about PID controllers. We'll talk about those in a future lecture. So now when the ball is disturbed, it'll start to roll down one of the sides of the mountain. The radar guns will measure the motion and through the controller activate the fans to resist and reverse the motion of the ball. And if I designed this control loop correctly, not only will this system be stable, but it'll have enough stability margin to account for any variations in the system and to reject unwanted disturbances, but it won't be so stable that the ball can't move at all. Now this is just one solution of many different designs that can accomplish this very same thing. And I'll admit that this one's fairly silly and probably a bit impractical. But that's one of the great things about being a control systems engineer. You aren't forced to stay with the same design for every single problem. In fact, you can tackle the same problem in different ways as sensors and actuators and materials change over time. For example, instead of a fan, we could have used springs attached to the ball that will impart a force back up the mountain. And instead of a radar gun, maybe there's pressure sensors in the mountain itself that can tell where the ball is. And so that's my question for you. What sensors and actuators would you use in this situation to create a stable system? I'd love to hear your ideas, so please leave a comment in the section below. Also, don't forget to subscribe because I put out a video once a week on control systems. And if you have any ideas for topics that you want me to cover in the future, please leave them in the comment section also. I'll see you next time.